We ended section 1 of this course with Bayes' rule, and that was a method that allowed us to compute conditional probabilities by saying, alright, we know we are given that the outcome is in one of several branches of a tree that we've drawn. So the total chance of those branches becomes our denominator. Those branches are our whole space. And then the chance of what we want is simply the chance of the subset of those branches relative to the chance of the branches of the given event. And that's a rather long-winded way of saying something rather simple. Recall the multiplication rule. It says the chance of A and B is the chance of A times the chance of B given A. You can use this as a definition of the conditional chance of B given A by simply rewriting. The conditional chance of B given A is the chance of A and B divided by the chance of A, and that's exactly your Bayes' rule calculation. In the denominator, you have the chance of what you're given, and in the numerator, you have the chance of what you want, but only on the set that is given. But you'll have noticed that many conditional probabilities can be written down without doing this kind of calculation at all. And typically, those are the conditional probabilities of what happens at a later stage of an experiment, given the results of earlier stages. And it's those more straightforward conditional probabilities that we're going to look at to discuss the relation between two random quantities and come up with a concept and some terminology that is going to be critical in what follows. And so we'll start, as always, with a simple example. I have a box with 5 tickets, 3 of which are red and 2 are green. Let's first look at an unconditional chance, the chance that the second draw is red. I'm drawing 2 times. I know I haven't told you whether the draws are with or without replacement, and for now I'm not going to. Can you find that chance either way? Certainly, when the draws are with replacement, you're drawing always from the same box, so the answer better be 3/5. What about when the draws are without replacement? Same or different? Are you sure? We went through this in some detail in segment 1.5. The draws are without replacement. You are not given anything about any of the other cards. So all of these 5 cards are equally likely to appear on spot number 2, and the chance is therefore 3 in 5, regardless of whether the draws are with replacement or without. This was the point of quite a long time spent on this idea way back when. And so if you look at unconditional chances, you can't actually separate with replacement sampling from without replacement sampling. Where you can see the difference is in conditional chances. And so we're going to find the conditional chance of getting red the second time, given that you got red the first time. And here it does matter, because if you are sampling with replacement, then your answer is 3/5 anyway, because you always sample from the same box. If you are sampling without replacement, and you know that you've lost a red ticket, well, then you have 4 tickets left in your box, 2 of which are red and 2 are green, and so your answer is 2 in 4, not the original 3 in 5. And if, on the other hand, you drew green the first time, if you're sampling with replacement, you don't care what you drew the first time. You are always going to say the chance of red is 3/5. But without replacement, if you lost a green ticket, then you still have 4, but now 3 are red and 1 is green. So the conditional chance of red the second time is 3 in 4 different, and different from the conditional chance. And so it is in the conditional probabilities that you notice the difference between with and without replacement. With replacement, the chance of drawing red the second time is the same no matter what has happened the first time. This is called independence. The 2 draws are independent. Without replacement sampling, chance of red the second time does indeed depend on what happened on the first trial, and that's dependence. So we'll write down an abstract definition of dependence in just a moment to make sure that the ground is solid beneath our feet. Let's look at, in practice, what we consider to be independent and what is dependent. So standard situations where you would be fine assuming independence: successive tosses of a coin, rolls of a die, draws with replacement from a box. That is what we were just looking at. Indeed, if you don't have a die, you could cut up 6 identical pieces of paper and write the numbers 1 through 6 on them, shuffle, draw at random with replacement successively, and that experiment would be probabilistically the same as rolling a die. Trials that are dependent, or equivalently not independent. The classic example is dealing cards from a deck. You deal without replacement. If I tell you that I got the ace of spades on the first card, then you know that I can't possibly get the ace of spades on the second card. Knowing what happened on the first did affect what you're going to say for the second. So the deck of cards and in general draws without replacement are the classic examples of trials that are not independent of each other. So in general, what is independence? Roughly, 2 random quantities are independent if knowing one of them does not affect what you say are the chances for the other. More formally, 2 events are independent can be given a formula definition. Recall what we just said. We said 2 quantities are independent if knowing that one of them happened doesn't affect chances for the other. Well, 2 events A and B are independent if the conditional chance of B given that A happened is exactly the same as the conditional chance of B given that A didn't happen. It doesn't matter whether A happened or didn't. Either way, you have the same chance of B. That makes A and B independent. And this can be written simply by recalling the multiplication rule, which is that the chance of A and B is the chance of A times the chance of B given A. If A and B are independent, then the chance of B given A is just the overall chance of B. It doesn't matter whether A happened or not. And that simplifies the multiplication rule. So a special case of the multiplication rule is when A and B are independent. And in that case, P A and B is just P of A times P of B. Conditioning B on A does not change anything. So let's take a look at a sample calculation just to make sure exactly where independence is coming in. So once again, I've got my 2 draws at random from our old friend, the box with 3 red tickets and 2 green, and now I want the chance that both draws are red. Yes, indeed, I do have to say whether the draws are with replacement or without. In either case, I want both draws to be red, so the first one has to be red and the second one has to be red. I'm going to use the multiplication rule in both cases. But what I multiply is different in the 2 cases. When you are drawing with replacement, here's the chance of red the first time, and here's the conditional chance of red the second time given red the first time. It doesn't matter what you're given the first time, so you're going to get 3/5 every time. Without replacement, 3/5 the first time, but now multiplication rule says conditional chance that the second one is red given that the first one was red. And that conditional chance is 2 in 4. And so independence does not determine if you are going to multiply. You are going to multiply probabilities if you are trying to find the chance that something happens and something else happens and something else happens. Is that fraction of a fraction of a fraction that we talked about in the last section. So where does independence come in? Independence comes in what you multiply. If your drawers are independent, the multiplication is typically rather simple. And if the drawers are not independent, well then you have to be careful, because your conditional probabilities change every time. So we'll take a look at 2 examples just to nail this down, and then we'll move on to a calculation that will stay with us till the end of the term. Right, a die is rolled twice. Can you find the chance that the first roll shows an even number of spots and the second roll shows 1 spot? I remind you, a die has 6 faces with 1, 2, 3, 4, 5, 6 spots on them. Right, so, well, can we do this? What does the first roll have to be? An even number of spots. What's the chance of that? Well, that's 2, 4, and 6, those faces, out of 6 faces. So the chance of that is 3 in 6, and so certainly. First roll shows an even number of spots times the chance that the second roll shows 1 spot. Does it matter that I'm not using conditioning? No, because the chance that the second roll shows 1 spot, given that the first was an even number, is just 1/6. It doesn't matter. If instead I say, I'm going to pick a person from a population, and in that population half the people are male and 10% are left-handed, can you find the chance that the person that I pick is a left-handed male? Well, then what you're going to do? One way to start is say, well, they've got to be male and left-handed. So fine, they've got to be in this 50%, and then times... I think you're going to get stuck. Because you want to take the chance that the person is male times the conditional chance that they are left-handed given that they are male. In other words, the proportion of men times the proportion of left-handers among the men. That number you don't have. And there you are stuck. It need not be reasonable to assume that the proportion of left-handers among men is the same as the overall proportion. It tends to be larger, actually. Gender and handedness are dependent. And so giving you these 2 overall population proportions of these 2 categories of people, and then asking you, well, what proportion are in both categories? That's putting you in a bit of a spot. You can't actually answer this question. And had you started the other way, 10% of the population is left-handed, so you start with a 0.1, then what do you have to multiply by? You have to multiply by the proportion of males among the left-handers. But you don't have that. So you are stuck. You actually need some measure of the dependence between these 2. Notice that you're not stuck in the sense that you can't multiply. You do want to multiply, you just don't know what to multiply. And that's where, had gender and handedness been independent, you'd have been in great shape. Unfortunately, the world isn't always that simple. So you have to ask the person who gave you the data for one more piece of information. Among the men, what percent are left-handed? And if they said, well, that's about 13%, then you would multiply the 0.5 by 0.13, and then you'd be done. But you can't multiply the overall proportions.